So welcome everyone to the Red Hat Research Days event on AI for Cloud Ops. We're very excited to have a conversation today with some researchers from Boston University, some folks from Red Hat, about a new project that is answering some very interesting research questions about how to operate the cloud, how to make it easy to do open operations, and how to take those actions in a way that we can have participation from a broad community of people in research. So we're really excited to be kicking this off as one of our collaboratory projects. And thank you all for attending to listen, and to our speakers for joining us today. I'd like to introduce Michael Clifford, who is the conversation leader from Red Hat. He is an AI engineer, a developer, a manager of software development, and also of software writing engineers, and occasionally even debuggers and systems engineers in the Red Hat CTO office. And he will be leading the conversation and introducing our other speakers. Thank you, Michael.
Cool. Thanks so much, Heidi. Yes, my name is Michael Clifford. I will be the conversation lead and moderator today. I just wanted to reiterate what Jen had said. If you have questions throughout the talk today, please put them in the session Q&A tab here in the chat. We'll be monitoring those throughout the presentation. Throughout the 90 minutes today here, we'll have a number of breakpoints where we'll have an opportunity for open discussion. So questions in there will be monitored, and also opportunity for people to join in the talk. And with that, I thought we could go around and let everyone introduce themselves. So why don't we start with the BU folks? I don't know if...
Michael is frozen, I think.
Oh, no. Have I been frozen for the last 30 seconds?
So you said, let's start with the BU folks. Should I introduce myself?
Yeah, that would be great.
My name is Ayşe Coşkun. I'm a professor at the Electrical and Computer Engineering Department at Boston University, and I'm the project lead for the AI for Cloud Ops project.
All right, my name is Gianluca Stringini. I'm an assistant professor in the ECE department at Boston University, and I'll be working on the computer security part of this project.
Yeah, so my name is Alan Liu. I'm also an assistant professor at the ECE department at Boston University. So I'm working on, network analytics and analytics engines, network measurement, etc. I'm happy to, participate and lead in this project. Thank you.
Marcel?
Okay, I'm not working at BU, but I'm working in Red Hat's Office of the CTO. I'm a manager and hacker for AI things and services and operations, and I love sim racing and playing Doom on the internets.
Great. Well, great introductions all around. So today I think, if at any point my internet stops, add a note so that I know that I'm not just into the chat, so I know I'm not talking into dead air here. But let's start off with Marcel telling us a little bit about the Operate First initiative and the vision for that project.
Yes. So it's AI for Cloud Ops. Heart, eyes, smiley, operate first. So I think I'm going to try to set the stage why we need AI for cloud operations, what stakes Red Hat has in this, in sponsoring this initiative, and also being invested in this initiative, and also why we lead up this Operate First community cloud and the broader initiative, and why we think this is super important for research and for communities and for open source in general. So this is my pretty face. I'm a senior manager out of Northern Germany, Kiel, working in the CTO office. And previously I worked on AIOps. I'm still working on AIOps, but now more with a focus on how do we bring open source to services. This is how we imagine AI, I hope, right? So we all anticipate the time where we can just be asleep at the wheel and drive through the car wash and whatnot, and do better stuff. And this guy on the right side is how we imagine people operating the cloud in the future, because there will be a self-driving cluster. So you can be asleep at the keyboard. So what drives me sometimes crazy even is that that we spend so much time in AI for identifying cat images, for talking to our smart devices. So I think AI has advanced in so many domains, but we're not really applying it to our own domain. So I'm seeing, when I started in venturing into this topic of AIOps, I haven't seen so much bleeding edge research in the realm of operations and applied to the computer stack as a whole. I mean, for sure, you see AI for some tasks, but not at the middle of the bell curve for doing operations in general. It's still pretty much all hands-on, advanced tooling, yes, but is there any automation built in where we defer the decision that something should happen off to an algorithm or to a deep learning model? Not so much. So this term AIOps, although AI for CloudOps doesn't mention, or that doesn't say AIOps, but I think it's still a little bit for like AIOps. So it's worth going back to this definition that Gartner created back in the days. I think they even started out with algorithmic intelligence operations. So AIOps platforms are software systems that combine big data and AI or machine learning functionality to enhance and partially replace a broad range of IT operation processes and tasks, including availability and performance monitoring, event correlation and analysis, IT service management, and automation. So that's a real bag of words what AI will replace. And maybe we can be asleep at the keyboard because the AI will be doing all that. But I'm not sure that we will arrive there anytime soon. So if you look at this curve here, this nice hockey stick curve, of course, where I just applied those prefixes from the self-driving car domain into the domain of AIOps, where we would start with assisted AI, something where a model or the intelligence helps you making some decisions, then over to augmented AI, where some decisions and some actions are actually deferred to the model without you doing stuff, and then finally to autonomous AI, where the AI is managing a larger environment or a larger subdomain completely on its own. And what we want to accomplish here is the number of systems per systems administrator, so that we get capable of running and operating more and more complex systems. Now, where can I buy it? I want to be at that right side of the hockey curve. So please, Red Hat, please, Mr. Vendor, give me that AIOps product. And that's my story and also my evolution over the past years. It's not really a product. It's more like a capability that you create via doing experiments. So you can't buy AIOps in a box, but it's something that you built in your team by expanding your horizon, by expanding your capabilities, how you approach certain problems. So I really treat it more like a cultural shift that we saw in this DevOps movements, where the developers took over tools from operations, and operations took over traits and methodologies from developers, and they created this DevOps movement. And SRE, site reliability engineering, it's an implementation of DevOps. I think it's the current culmination of coders that also operate large systems at scale by applying best principles from the development domain into the operations domain. Now prefix that with AI, and you get AI DevOps or Aiops. So it's more like reaching into the tool belt of the data scientists to solve that problem of ever-growing complexity in the cloud. And that's what this cloud age brought us, where it's not so much anymore about the software and the features that the software gives us. Obviously, you want also those features because you want to get your problem solved. But weighing in, it's probably equally or maybe more important that the software, the service, the features are actually available, and that they are available at scale. So if the value is more in operations, and operations are by definition proprietary, then open source as a whole has a problem. And this is something that we tried to address with Operate First. And I think it also really is supportive of the AI domain, which I'm closing the loop to later. But here's this contributor funnel of open source software, where you have 100 users of a piece of software, which eventually turn a subset of those users into actual contributors. And at the way down to that funnel, you also leave your marks in contributing to the software itself by just using it, or by opening issues or leaving some questions on forums, on Stack Overflow, etc. And that is being essentially tried out with a software as a service in the cloud age, where you essentially stop at the API layer and you cannot really contribute to that service anymore, because a lot of the stuff is also part of the operations domain. So Operate First is a concept to incorporate operational experience into software development by extending development to including operating, testing, and proving code in a production environment. And that's what we try to set out with this Operate First community. Really create something where all these personas that make up a service, that make up a complete solution, which is larger than something that I can install on my laptop. So it includes people that actually operate stuff, the platform, but also the workloads. Then developers who create parts of the platform and parts of the workloads running on that platform. Obviously, you want to have users, because without users, you would have just a lab environment or a unit test, which is something that we already have, but you really want to unleash those chaos monkeys to your software to find those edge cases. You want to have people from support, so that you make sure that your software gets actually usable by users. And you want to address architects that use parts of that platform as building blocks and create something new, and create new versions of something. Maybe exchange this building block with another building block and have these running side by side, adding more variability to it. And eventually we also have those robots operating that environment for you. So that Operate First cloud environment at operate-first.cloud is really a hybrid cloud environment with full visibility into the operations center. And it's real. You can access it already. A large part of it is in the MOC data centers, but there are also other environments in that larger hybrid cloud thing. So really quick rundown through what the systems are comprised of. So as I said, in the MOC, there's a larger cluster. We have some cluster running in the German stack rack space equivalent called Hetzner. We have some deployments in AWS, and we are working with other providers to also add resources to that larger setup. So we have created an environment which is not really small, and it acts like a production environment, but it opens the opportunities to treat it as a greenfield project, to practice really leading edge technologies and try out stuff without running into troubles of violating SLAs or such. Obviously, there are also some workloads there. Open Data Hub, one of the larger workloads with Jupyter notebooks and Kafka and other AI stuff running there. We have a lot of management tools like Advanced Cluster Manager, Argo CD for doing GitOps, Tecton pipelines for doing build pipelines. We treat everything as a service and as an operator. So every part of the platform should be reused by other contributors to the platform, so that we create such a mesh of building blocks that use each other. And obviously, we also want to create operational data, which leads back into this project AI for Cloud Ops, because data is a fundamental building block for doing AI these days. Because otherwise, you will have synthetic data which doesn't reflect the real world. And getting to real world data, as I explained previously, is kind of tough because operations is proprietary. So in that community, we can create, and we're already creating, larger free data sets of real operational data, which we can also manipulate, and where we can poke the environment and introduce failures and stuff. So really, AIOps in a community is about the discussion, the collaboration, the how do we get to standards, and growing together and democratizing operations, so that it's not just the shared secret of one entity that knows how to operate stuff, but that should be the common building block for everybody, for the whole community, knowing how to operate things at scale, so that your own data that you build on top of it becomes your actual competitive differentiator, and not the foundation of cluster locks and such. And with that, I'm at the end of my small slice here, and I hope I made clear why Red Hat is interested in redefining or re-envisioning what open source did to software, to proprietary software, and redefine that in the cloud age, where we are faced with proprietary data, with proprietary operations, and bring the open source community aspect to exactly this domain. And at the same time, enabling AI projects to fruition.
Awesome. Thanks, Marcel. So yeah, at this time, I'd like to open the floor for any questions that anyone in the audience may have. I think you're able to join in the chat, share your audio and video if you want to ask a question, or you can go ahead and ask it in the Q&A and look at it here. So somebody asked, are there some examples where we're currently using AI in operations?
If the question is we, yes. So there, like I said, the hyperscalers are certainly using AI. So Facebook probably has AI optimizing the energy consumption of their data centers. In the operate first area, Michael led a team where we used machine learning to identify the best profiles for using Jupyter notebook images. So before we just had small, large, and I don't know, default with 2 cores, 4 cores, 8 cores, and actually using or looking at the usage of the Jupyter notebooks, we could come up with better templates, better defaults for using these notebook images. Is that really AI operations? Maybe, maybe not, but it's certainly using data science and statistics to an operational problem where before we overcommitted the resources in that cluster, and now we did a data analysis by collecting data and then making it more worthwhile and more applicable to those usages. Red Hat is doing this remote health monitoring for OpenShift, where we collect telemetry from clusters out there, and we're sending them back to Red Hat and actually identifying problems in clusters at customer sites through the means of data science. Again, is that AI operations? Not really, because we are not operating these clusters. But then it's applying AI and machine learning to a larger data set for identifying operational problems at customer sites. So I think what I'm getting them at is AI ops. Sorry if I talk too much. AI ops is more than just operating stuff with AI. It can be the whole spectrum where you use machine learning for operations.
Awesome. And so we have another question here. At the moment, what are the demographics of users on the operate first environment? For example, is it mostly academia? What is the distribution type of users on the platform?
It's a good question. I only looked at the size of users. We had 250 unique GitHub handles accessing the platform. I would say it's mostly Red Hatters these days, with a large portion from the Boston University, because that's where this initiative has been incubated.
Cool. And someone else asks, you mentioned your own data as a competitive differentiator. How would you prevent that mindset from discouraging open data sharing among cloud users and companies, especially since AI typically does best with as much training data as possible?
Yeah, maybe I need to update that slide. The idea was that your own data, as in your business data, should be the differentiator. So if you're selling shoes, keep the shoes data to yourself, but don't try to differentiate on data that drives your shoe selling platform, because that's common among car sellers and coat sellers and other clothes sellers. So the shoe data, that's your own data.
All right, great. I think we've done a good number of questions here. Hopefully there'll be time at the end to answer questions. I have just one for you, Marcel. Like, how many years away are we from the self-driving cluster?
My Garmin watch predicts 4 years and 3 months and 40 seconds.
Perfect. All right, great. So now we'll hand it over to Aiops to discuss some details on the project that they'll actually be collaborating with Red Hat on.
Thank you, Michael, and thanks, Marcel, for the great introduction. I'm Aisha Joshkun. I'm a professor at BU in the EC department, and I'll provide you the general overview of the project and what motivated us to start with. And we already introduced ourselves, but I'd like to also acknowledge, in addition to Marcel, Steven, and Daniel from Red Hat, and Fabio from IBM Research, whom we've been collaborating for several years now. And we already have several PhD students on this project, and I believe all of them are in the session as well, and so they might jump in to answer some questions later if need be. Anthony, Mert, Saad, and Leslie, thank you for joining. So the next generation of cloud computing, when we look at it, we see that most innovations are driven by efficiency and scale. So that means we would like to build faster, better, cheaper systems that work at scale. And automation, broadly, is the way to go to make this actually cheap and at scale, because we'd like to reduce the expert dependency in monitoring and management of these systems, which we call ops, cloud ops broadly, as much as possible. So we believe AI is the next logical step for this, to circumvent the slowest and most expensive element in here, which is the human operator. So adding more humans doesn't necessarily make things more efficient. It doesn't scale well, and it's really costly and slow. So we'd like to use AI to recognize known problems, make decisions to, for instance, resource management decisions, as was just asked in the Q&A session. And we'd like to make better ops decisions to improve performance, efficiency, security, and resilience. And many other examples can be given in terms of operations to make cloud faster, better, cheaper. So why AI? Marcel already talked about this, but basically we see AI virtually in almost every application: image recognition, speech recognition, robotics, navigation, finance, and many others. And all these domains make very successful use of AI today. So this is partially due to the maturity of the field of AI at this point. So we have great tools and methods that can be applied more robustly today compared to just a decade ago. So we believe that's partially why it's time. And when we look into the status of computing, computer systems, though, is that even though machine learning, using machine learning requires having at least one computer or more, when we look into the computer systems themselves, we see heavy manual administration still. So manual administration could mean somebody physically going into a computer room, which happens to some extent, but more often than that, we have experts writing scripts, domain-specific scripts to manage systems. So what do these scripts would be doing? For instance, let's say you want to identify what applications are running on your cloud, and your expert writes a rule saying that if this file name at this file size exists, that's going to tell me this particular file exists in my cloud. And later on, if this application you just detected is vulnerable, or if it's buggy, or it needs to be updated for some other reason, or maybe for compliance reason, you don't want to let this application run on your cloud, then you can basically manage it that way. However, we are talking about a cloud system today where we see hundreds or thousands of applications getting updated on a daily basis. So software is no longer coming from a few well-vetted sources. Software is coming from everywhere. Hence, lots of updates, cloud changes on a daily basis. So this rule might become irrelevant if this file changes with today's software update. And then your rule to detect whether this app is running, if this package is available in your system, no longer is valid. So you can see how fragile manually written scripts get pretty quickly. So your experts now need to maintain all these scripts for all the applications, for all kinds of problems. So it gets out of hand really quickly. So as cloud has already grown beyond what manual operations can manage, we are working on ways to automatically optimize efficiency and detect problems in resilience and in security in cloud applications and infrastructure at the same time. And in this way, we'd like to lead the path to higher performance, more reliable and secure operation. Now, we have a project website up already, so you can check us out there. And you are also encouraged to sign up on the Operate First GitHub. There's AI for Cloud Ops project already, so you can follow our updates from there. And now this is the kind of framework we'd like to build. So the cloud system has applications, platform layers, and underlying infrastructure. And there's a lot of data available in these different layers. And telemetry data, information about files, information about different types of logs. And we'd like to aggregate all of these into an analytics engine in an efficient way and provide this data through unified APIs to our analytics tools. So you see some names here: Praxi, Wave, Tritium, security tools, and we'll give some examples of what these analytics tools look like in a little bit. So the idea, though, is that through a selection of analytics tools, we would like to feed this back into somebody working on a Jupyter notebook, a developer who's going to deploy on an Operate First cloud, their Jupyter notebook that's doing some data analysis and the like. And we'd like to see the analytics working with the developer during development, during deployment, and while running the system as much as possible. Or similarly, you might be already using Thoth, and then our analytics tools will be available over there so that you can work with them. So a differentiating factor in our work is that we'd like to get the cross-layer data. And this is a research challenge because this needs to be done in an efficient and scalable way. And then we'd like to feed this back to the users and administrators in an easy-to-use way. So our vision is to have this alive framework for the community. So not just the tool set that we are providing you to work on, but you should use it and contribute back with the problems you're observing, your analytics engines and the like, and you can plug them back into the framework. And of course, this is enabled by open sourcing everything, which we'll start doing right away. Some of these analytics tools will be available for pre-deployment. I'll show some examples of right when you're coding, the analytics tools already can identify potential problems, vulnerable packages and the like. And some of the engines will be for runtime analytics, such as doing efficient tracing to debug a performance problem, or doing security or network analytics and the like. And like I said, in both cases, you can, and you actually are very welcome to plug in your own engine into this system where you have the data coming from real world sources already, and then you can write your engine for the type of analytics that you'd like to do for your ops. And all this will be available all the way to the user, who is basically just coding, and then analytics will be visible to the user so that they can improve their coding and solve problems like, why is this code now suddenly so slow? Or why is the system now crashing and it wasn't crashing just 2 days ago? And we will also use existing infrastructures like Prometheus and the like, and then we'll put in more efficient ways to organize telemetry data. Ellen will talk about sketches in a little bit. So our vision is that, like I said, you start writing your Jupyter notebook, you're writing some code, and the code analysis and software discovery will be available even before deployment. So what is software discovery? It's basically letting you know whether a problematic application exists in your code. So in this case, for instance, the analytics tool would say that, hey, this module is outdated, you need to upgrade it, or there's a vulnerability, known vulnerability here, you need to fix that, or you need to change what you are doing with that package. Or through synthesizing the software discovery with the runtime analytics, the Jupyter notebook, you can actually see that this line of code, or this chunk of code, or this function is responsible for this performance problem you are experiencing right now. So how is this happening? The magic behind this is the Aiops Engine. And like I said, we'll just show some examples on how this Aiops Engine would work for different kinds of problems in just a little bit. So the user or the developer will be also able to see runtime analytics through our framework. So let's say you have some instances, you are doing some data analysis, you have different versions of this code, and then you can see in the framework we are going to provide what is running already, what is scheduled, what is successfully completed, and what's unhealthy. And for instance, unhealthy could mean that one of your instances is doing a lot of excessive resource usage compared to its normal status. You can also see typical telemetry data regarding how your code is using the CPU, the memory, and the like. But the nice thing is that all of this will be synthesized and then fed into analytics engines already to give you more meaningful feedback than just showing you raw data, while raw data will also be available in easy to navigate way. So one method to debug systems today is tracing. And here you see a graph, colorful graph, and each triangle or circle, etc., with different colors shows a different entity. It could be like a pod and a container or a service and the like. And traces basically give us structured log data, right? And we'll show you some ideas on how we'll make tracing better, and then how we will unify that with telemetry using efficient methods. And then the system reliability engineer, for instance, can look into runtime analytics and see what service, what request had an error rate that's high, or which one actually slowed down compared to its normal execution. And then this gives you a lot of information for when you are debugging your problem, as opposed to starting blind. And trying to debug a distributed system is a hard problem, as many of you might know. So what are some examples of these analytics engines that are doing the magic, basically, to identify software or identify known problems at runtime and the like? So as cloud applications become more important, more complex over time, we think it's really important to have the right kind of software and code discovery tools in place. So we've designed a tool called Proxy, which is a fully automated machine learning-based tool that captures system information into signatures or fingerprints based on what files the system is changing or adding upon an installation. So it looks at file names, creates some fingerprints out of these using some hashing methods, and then basically you have a fingerprint for each application installation. Later on, you can have a database of known problematic applications or maybe applications that are not allowed on your cloud for some reason, applications that are vulnerable and the like. And then whenever there's new software being deployed, even before deployment, you can actually check, hey, you have these packages and you need to fix them because there's a known vulnerability with these. We demonstrated that this type of machine learning based method is fast and it's accurate and it offers a lot of potential. In a similar path, we designed ACE, which is approximate concrete execution, which is basically, as opposed to looking at file names, this time it looks within the code and gets a chunk of code and executes it on a really efficient small engine and creates a fingerprint based on that function execution. Now that fingerprint later on, as you see in the figure also here, can be compared against a known list of functions, again to determine maybe some unwanted code for vulnerability, security, resilience, etc. reasons. So we again demonstrated this type of technique to be accurate and fast, and it reduces the amount of, the way we design the system reduces the amount of a priori training that you'll have to do on the system. So both of these methods, by the way, are already publicly available in GitHub repositories, and now we are going to scale them and apply them in the context that we've been discussing using operate first environment, using Jupyter notebooks and the like. So I'd like to give one more example before leaving the stage to Alan and Gianluca, and that's WAVE, variance-driven automated instrumentation framework, where we have designed methods to automate tracing. So this is basically a logging framework that determines where and when to instrument. So what is tracing? You can place basically hooks into your distributed application and get information, and later you can use this information to debug problems. Now, the issue with that is that if you wanted to trace everything that's possible to trace, you can imagine that the overhead will grow into an unmanageable level really quickly. So instead, we'd like to do something intelligent and only increase instrumentation where it's needed. So we already have some methods that are looking into statistical differences compared to normal or similar status of some services and increasing instrumentation in there. And we use distributed tracing, such as Jaeger, as an enabler for this. And on top of that, we design our own instrumentation plane and control plane, basically that's deciding on where to instrument and then enabling and disabling instrumentation in the application as needed. Now, our current work is basically looking into bringing more intelligence here so that we can continuously run such frameworks without necessarily having to go after a problem, but continuously collect the best tracing information possible at an efficient way, that at an overhead level that's acceptable. And then we can use this information to diagnose all kinds of issues in the system. We demonstrated with HDFS, with OpenStack, with DeadStar Bench applications, when we inserted problems regarding slow code, resource contention, and problematic third-party code. By enabling only a very small percentage of the available instrumentation, we can still diagnose problems. Now, like Marcel emphasized also, data is the core of all this analytics. You cannot do analytics if you have no data. And there's ample data, actually, when you run a system. But first of all, there's the availability issue, and then we hope to get over that by using this operate first environment where we have a lot of real-world data. And the second issue is that there's a lot of different kinds of data. There's file data that I mentioned, there's code data, there's tracing data, there's telemetry data. That's lots of time series coming from different levels of the system. Now, one key part is to do this data collection and fusion efficiently. And next, Alan is going to talk about how to use sketches for getting efficient telemetry data from the infrastructure. So that's all for me for now.
Cool. Awesome, Ais. Thank you so much. That was super interesting. We already have a few questions in the Q&A here. So again, just to let everyone know, we'll be taking I guess, break from presentations to have some questions. So please go ahead and add any questions to the Q&A side channel. While people are adding questions there, I have a quick one for you. Like, given the vision that you've outlined above or like earlier, like how do you see the role of a DevOps engineer or like a cloud native engineer evolving with all of this kind of tooling in place?
That's a great question. So I believe we are quite far away from the sleeping on the computer example myself give. And that's not the intent. Basically, the DevOps engineers or the site reliability engineers, they are not going to be completely eliminated, at least for a long time. But their role will be doing more targeted, more insightful, doing work based on more insight given specific to the problems that their code might be experiencing and the like. For instance, like I said, software evolves really rapidly, and you can go and try to make your system better using a lot of rules of thumb, standard profiling tools, and the like. But what if the system was telling you, hey, you know what? This between version 5.2 and 5.3, this code block that you introduced is actually causing most of the contention you see here. So this is really good information. Then your DevOps engineer can act on it with much more insight, and it's going to become a lot more efficient. So this is the kind of thing that we see. And in terms of contributing, the more information we have about what kinds of problems are the most important or most difficult to debug, the better we can tune our framework to solve these most difficult problems using AI. So we'd like all the feedback we can get regarding what problems people are seeing, what are difficult things for them to solve, so that we can, make sure that we are addressing those problems.
Cool. Awesome. Yeah, we have another one here. Can Vaif and Ace do this with containerized workloads, like, for example, on Kubernetes or OpenShift?
Yes, certainly. Ace actually, we applied it to containers, we applied to microservices. So wherever there's code and you have a mechanism, and we provide the mechanism basically to fingerprint the code at the function level, if that's desired, then we can do it for containerized workloads as well. And similarly, Vaif is a tracing method that's looking into basically collecting traces efficiently. So as long as you have a distributed application where you have the ability to place hooks, to place trace points, so to speak, then you can do this. There's no barrier for containerized workloads.
Cool, awesome. And yeah, we have one more question here. So how does the fingerprinting work when, for example, the same source file creates different bytecode / assembler depending on the compiler used? Also, file names could be changed. For Java libs, we often add a -Red Hat part to the library name.
Yeah. So that's a great question too. So this is in relation to the method I described that's called proxy, that's looking into file names to create hashes or fingerprints to recognize software. So the second part of the question, basically, file names could be different. True, you can add different paths, but we have mechanisms basically to remove the path and look into the file name alone. And the method is not 100% precise. Basically, it's creating hashes. So if there are some differences in the file names, then it can still generate a fingerprint that fits the original fingerprint, or it creates a very similar fingerprint at least. Of course, if somebody comes in and changes for an application all the file names into different file names for some reason, then this method is unlikely to work successfully. But normally, unless there's a special intent to change all the file names, we don't see this kind of thing. There are, like the question says, there might be a Red Hat part in the library name and things like that, and we can get over that by using this hashing method. And when the same source file creates different types of bytecode, depending on the compiler, I guess, that's a question related to the other part, like looking into the code, the function level fingerprinting. And yes, the different compilers basically can use different bytecodes. That's correct. We tested across different systems. But at the end, the approximate execution engine for the same kind of functionality, the intuition is that it's going to generate a similar fingerprint, even though it may not be the exact same fingerprint. But of course, the method needs to be tested for what if different compilers, with a broader scale, what if there's different bytecode and the like. And these are interesting challenges that we intend to work on.
Awesome. With that, I think there's a few other questions here, and I will save some for the end, but to make sure everyone has the opportunity to get through the presentation, I think, Ellen, if you want to take over and start sharing.
Yeah, hello, everyone. Yes. Can everyone see my screen?
Yes.
All right, sounds good. So I'm Alan, so I'm an assistant professor at Boston University. So today I'm talking about network analytics, right? So as part of our proposed analytics engine, so we need to look at an important and also massive amount of data in the cloud, which is the network data, right? At its core, we want to build a runtime and analytical capabilities to enable and enhance the AI for cloud apps. So why we need to run this like runtime network analytics, right? So we want to talk about this AI for cloud ops. A key underlying workflow to me is we need to do automated closed loop control, as Marcel and Asher mentioned a lot of times, that we need to collect this analytical and telemetry data, and then we can lead to AI-based control for performance evaluation, to failure detection for security analysis, etc. Right? And at sometimes we also need to go back and zoom in and additional analytic data to make sure that we make our control and decisions correctly. So among all this data, right? So if we can collect and analyze this data at a very timely and accurate manner, and we can handle these anomalies, right? Quickly, we can make the system more reliable. And then why it is a difficult thing to perform such network analytics? Because the network data is everywhere. It's in distributed systems, in the cloud. It's across different layers. It's between different applications, Jupyter Notebook, etc. Different platforms, Kubernetes, OpenShift, and also underlying infrastructures, right? The data is just moving around. And we want to measure a lot of things as well, right? We want to obtain a lot of statistics, understanding what's happening in the network. It is just naturally infeasible to store everything. And it's very complex to perform online analysis to obtain fine-grained statistics. For example, people might care about as an operator that, oh, I'm experiencing high latency, what's going on? And can we detect some low throughput happening between a pair of users? Is my network under attacks? Am I experiencing network failures? Or underlying of this is a complex network analytics. So our key idea here is we want to build a cross-layer, fine-grained online analytics engine with optimization algorithms, like we call sketch algorithms, to perform online analytics, to enable automatic closed-loop control. So unlike the traditional approach we've been seeing around like NetFlow and AskFlow, it's fundamentally changed the way we perform analytics. Because it's not just to collect data and then perform analysis. Sometimes we just need to analyzing the data on the go. So at the high level, the sketches are, can be deployed as like lightweight data structures to the platform's applications. And when the data stream, like network traffic, system network logs come, we can maintain this data structure as a summary of the data. And then we can query a lot of different kind of statistics, like heavy hitter users, heavy hitter network connections, the entropy of different network traffic, the number of unique users and flows, etc. So we can also combine these different data structures and to obtain aggregate global statistics as we need. You might hear about, you might be curious about how sketches work. It seems like a magic. But let's look at some very simple data structure being proposing around for a decade. So for example, like if we want to estimate the heavy hitters and heavy hitter users in the network, then we can maintain certain we call company sketch, the simple data structure here, using a multiple independent hash indexed tables to preserve the flow sizes, right? So every packet you get is key, for example, the source IP address, and then we insert it in independent hash functions into this table, just like similar like counting Bloom filters. And then this data structure can accurately preserve the flow sizes on the go. So it's been proven theoretically and empirically that they can preserve very high accuracy. So this is just a very simple example how this such data structure look like. And in this direction, we have been building some more advanced, more complete sketch data structure to estimate a wide range of metrics and then can work for multiple different dimensions in the network. So for example, one work here is we call the Unimon or universal monitoring step, and where we can design and then deploy sketches around the network. And then it can, when you do the estimation, we can gather the statistics from all this vantage point, and then we can query the statistics at the runtime that, any kind of the statistics that's supported, and then we'll fetch this information, put them to different applications in that operation, right? Just a concrete example here, this structure can be as small as using like 600 kilobytes of memory, while still can estimating a broad range of metrics like entropy and heavy hitters, flow size distribution, etc., with 98% of accuracy. So in these particular examples, we are already processing using 600 kilobytes, processing over 16 million records. So another example here is we call Cocoa Sketch. Because the network data are naturally multidimensional, so there will be many packet header fields that we care about. For example, like a source IP, destination IP, source port, destination port, or even the application layer tags about HTTP, about certain, key value storage, etc. Can we query statistics about all these header fields? So we call these header fields as keys, and then we want to measure arbitrary keys on the network on the fly. So then it's keep imposing some challenge here, because the universal monitoring, you just see that we can estimate different statistics, but it's only for one key at a time. So we build a Cocoa Sketch to support arbitrary keys, and we don't need to predefine what kind of flow keys are of interest in the beginning of the measurement. So, and then, for example, if we query source IP that's sending a lot of traffic to many destinations, is this the malicious code that running on your system? Is this a malicious user? Then we can diagnose. So then you see like multiple examples that we can collect different metrics from the network from different dimensions. And then this is the future time. We need to using this data to, for example, here, we want to perform failure detection. So we obtain so many data, and we want to train a very fine-grained machine learning model using sketches, right? Because sketches, we can apply sketches into a federated learning paradigm to perform online learning to improve the training and inference cost significantly. Why? Because the sketches are tiny in size, you see like 600 kilobytes, but they still preserve a lot of features you care about from the network. And then when you do the queries and you do the inferences, you only need to put in the sketches, right? To improve the speed, to improve its real timeness. And then finally, we hope this make a steady step toward, finally, we can automate it, our AI for ops. So yeah, I'm ending my part now. I'm happy to take any questions. Thank you.
Awesome. Thank you, Alan. Yeah, so any questions in the Q&A? So I mean, while people are going in there, I have a couple questions for you. So can sketches support all kinds of metrics of interest that we care about?
Yeah, so this is a great question. So for the sketches, we already proven, and empirically as well, like it can support a wide range of statistics, but definitely it's not everything. There's no perfect algorithm support for everything. I think it's also the part of our research that we want to work with Red Hat. We can understand, what are the metrics of the most important in the daily operations, and then join the community of operation first to understand this metric, right? So we have our own mindset right now. This is some of the metric that could be useful, but ideally it needs the joint insight from the algorithm side, from the system side, from the operation side to define, this is the metric. And then we can possibly improving or even developing our new algorithms, plugging into the software stack and to measure the new metrics. That's the.
And so like, how does this compare to some of the other network telemetry and analytics approaches that are currently deployed?
Yeah, so yeah, the good question. So for, I directly mentioned there is a lot of, industry standard like a NetFlow AdFlow plugin. It's adopting this, like we collect some sample data and then we do the analytics on the fly. And the fundamental difference is we are leveraging this new algorithms and performing it online. And it's been proven that, we don't need to store a lot of data, but it still can provide highly accurate data, like accurate results for the daily operation needs, right? So we don't need, for example, if in a data center, you are presenting terabits of data at the entire set, and then even you're sampling 1 over 100, you're still storing a quite amount of data each day or each hour, each minute, right? So how we can make it fully automated? We are looking at the data seed, and then we can find the needle. No, I mean, it's not really possible. So we kind of wanted to tailor it into, most important metric we can do, and then we put it in the online fashion and in accurate and low resource footprint. And then it could be a use for enabler for later, let's say, self-driving management, right? We cannot just, the self-driving car is not, I couldn't just look at all the data from, millions of drivers every second. I don't think that is a feasible path. But I think we tailoring this online fashion, we tailoring to this, a subset of the most important metric will be a steady point towards the next step. Thank you.
Cool. Yeah, cool. Awesome. So we have one question in the Q&A here. So with distributed networks between data centers, can you still use sketches successfully, even though many routers aren't contributing to the sketch?
Right. So that's actually a great point. So I think this is also part of the motivation when we started on researching in this direction is we want it to be naturally distributed and later it can be aggregated online. So it's theoretical guarantee also proven that so we can deploy this subset of this sketches everywhere, even across data center distributedly. And then because they're so tiny, you can periodically gather them together, and then it can be perfectly aggregated together to obtain merge the result. That result can also get, has a good feature tell you, oh, this is the good measurement towards everything that you collect here. So this is a very unique and advantage for the search-based kind of analytics.
Cool, awesome. Well, thank you. Any other questions? All right, well, in that case, we'll hand it over to Gianluca to give the next section of the presentation.
All right. Thanks, Michael, and hi, everybody. Again, I'm Gianluca Stringhini. I'm an assistant professor in the EC department at Boston University. And broadly speaking, I work on computer security. So now I want to share with you a couple of ideas on how could this AI for cloud ops approaches be used to tackle security problems. So the main difference between security problems and other types of problems like performance and whatnot is that we have an adversary, so a malicious person who's trying to do something bad to our infrastructure, our systems, and so on and so forth. And just for the sake of example, I will consider two separate threat models that we could assume for our deployments. The first one is legitimate users of Jupyter notebooks in an operate-first environment who just make mistakes. They might use insecure modules, they might introduce security vulnerabilities, and so on and so forth. And these could be later be exploited by others, for example, through a malicious file or something like that. The second threat model is actually a malicious user who might write bad code, malicious code, with the goal of compromising the security of the cloud infrastructure, so perform a denial of service attack or worse. So how do we deal with these two problems? Well, the idea is to collect telemetry data, telemetry events generated by Jupyter Lab notebooks, similar to what was discussed earlier by Aisha as well as Alan, and then use them to train AI models, and then use these models to detect potential attacks and potentially predict them ahead of time, so that we can be one step ahead of the attackers and do something about them. So what does vulnerable or malicious code look like? Well, there are two types of vulnerable or insecure code that we can look at. So one is just known vulnerable and insecure modules. There can be function calls, there can be libraries that have vulnerabilities, and these include code injection, they include untrusted data serialization, they include insecure cryptography, plain text network functions, or using weak cryptography, and so on and so forth. And the second type are actually code blocks, where the single instructions may not be malicious by themselves, but if put together, they could perform attack. And the very simple example here, for the sake of explanation, is the fork bomb, where you just keep forking until you exhaust resources and so on. So what we're planning to do here, we are planning to execute these code blocks, and as they execute, we plan to collect telemetry at a number of different layers. So we plan to collect memory data, file accesses, network data, access logs, all these things that Aisha and Alan have been mentioning already. And then we plan to use this telemetry to train different AI modules, potentially labeling them with a benign or malicious label based on what we've observed in the past and so on, and then produce trained models that we can use to actually improve the security of our systems. And we can use these trained models in two ways, mirroring the deployment approaches that were discussed before. So we could have a pre-deployment type of operation where we actually warn the user, look, this code that you're trying to use, we learned in the past that is malicious or could be used maliciously and so on. So please fix it. And the second one is at runtime, which works particularly well if we assume malicious users in the loop. So as the code is executing, our models could see if the code execution is leading towards a malicious state, and then we could, for example, kill the process or something like that. So to give you an example of a project that I worked on in the past in a slightly different domain that uses some of these ideas, this is the Tiresias project that was designed to predict security events upcoming in intrusion prevention system logs. And then I will discuss how could we apply these same ideas and improve them to work in the cloud scenario. So the idea here, this was a project in conjunction with NortonLifeLock. So they have real-world intrusion prevention systems running on corporate computers. So these are regular Windows computers or Linux servers and so on. And these collect security relevant events. So this could be, a port scan. It could be the exploitation of a certain CV, and so on and so forth. Modern attacks tend to be multi-steps. So an attacker might, perform a port scan, identify vulnerable service, exploit the service, then do some lateral movement, do some execution, some escalation of privileges, and so on and so forth. So the idea here was to collect all these sequences of security events that clients were observing, use them to train an LSTM model, so recurrent neural network, and then use that recurrent neural network to basically predict, given a sequence of security events that we are observing, what the attacker will do next. So the idea here would be to be one or more steps ahead of the attacker, to be able to deploy proactive defenses instead of reactive ones as we are used to. And so what we had here, we had over 4,000 possible security events that could happen. And our system was actually very efficient in detecting them, in predicting them. So 85% of the time, we would predict the specific security event out of over 4,000 that would happen next. And if you would generalize this and just say, instead of predicting the specific CV that will be exploited, but just the category, let's say next there will be a remote code execution or something like that, we would be even more precise and so on. So how do we take this idea and apply it to the cloud? Well, what we are planning to do is to leverage the telemetry generated by the execution of code blocks in Jupyter notebooks to train a model, for example, an LSTM model and so on, and then use that in two deployment types. So we could use it in pre-deployment mode. So as the user is writing new code blocks, we could match them using fingerprinting techniques similar to what we discussed before. And then warn the user, look, this code was deemed to be malicious previously based on our observations and so on, or vulnerable and so on. And the second one is run at runtime. So as processes and code blocks are executing, we would be running our model, and our model would predict what happens next based on previous observations. And if it predicts that an attack is happening, proactive measures will be taken. So the process could be killed, it could be rate limited, and so on and so forth. The second example does not deal with detection or prevention, but deals with understanding what attackers do on real-world systems. And so this is the attack-to-vec system, which takes as input the same kind of security events that I was talking about. But the idea here is understanding how single attack steps are used in the context of others. So if we have a single CV being exploited, that single CV is likely to be exploited as part of a multi-step attack. Can we learn what are the typical multi-step attacks in which that CV is being exploited? And the way we do this, we borrow techniques from natural language processing. So we use vector embeddings. We basically consider a single security event as a word in a sentence, and we look at the other security events that typically happen before and after as its context. And by doing that, we can learn the typical way in which certain vulnerabilities are used, but we can also identify sudden changes in which a certain security vulnerability is exploited. And that could indicate that attackers are changing their way of operating. They maybe found a new successful way of exploiting a certain vulnerability, and so maybe we should adapt our defense strategies based on that. Just as an example, so we looked at the Apache Struts remote code execution vulnerability. The CD is on the slide from back in 2017. And what we did, we looked at how that specific CV was exploited in conjunction with other attack steps over time. We calculated the vector embeddings, and we applied cosine similarity to see how stable this exploitation was over time. And what we can see here is that as the CV was released, there was a lot of variability. So the exploitation wasn't very stable. The cosine similarity was low because attackers were trying to figure out what worked, how to exploit this vulnerability reliably. Later on, the exploitation of this vulnerability becomes more stable because attackers found, a working weaponization, a working chain of actions that actually could exploit this vulnerability effectively. If we later on saw another steep decline in the cosine similarity of how this CV was used, that would indicate that attackers had found a different strategy. And then we would need to factor in that strategy into our defenses. So how can we apply these ideas to the cloud? Again, we could match code blocks to previously observed ones and basically look at the context in which these code blocks are executed. We would look at a sequence of code blocks and so on, especially malicious ones that we identify to be malicious. And then this would provide us situational awareness. If suddenly we would see that a malicious code block starts being used in ways that we've never seen before, then maybe we will need to have operators look into that to figure out what attackers are doing and use that to develop better mitigations. So yeah, this is what I had, and I think this is our last slide actually. So I'm open to questions. Thanks.
Cool, awesome. Thank you so much. So so any questions people have, please add them to the session Q&A. I saw a couple slip through to the event Q&A. We can return to those in a minute here. We're waiting for that to fill up. I mean, I have a particular question. I think this is really interesting. So you said that, right, you can treat a single attack step as like words in a sentence. So you're suggesting, right, that there's some kind of like grammar essentially to a malicious attack. And that just seems like a really interesting insight. Like, can you speak a little bit more about why you think that what works for predicting the next word in a sentence should work in the domain of like malicious threat detection?
Yes. So first of all, intuitively it makes sense because single attack steps have a semantic meaning. Attackers are trying to do some reconnaissance, then they're trying to get a foothold in the organization, when they're trying to do lateral movement, and they're trying to escalate privileges and exfiltrate data, whatever they may be trying to do. So it makes sense that sequences of attacks actually happen in a similar sequence, at least successful attacks. Then we did some analysis, and we had millions and millions of events, and we found that basically these attack steps follow the same properties as words in natural language. So there will be some of them that are very common, some of them that are very rare, and so on and so forth. Now, I should say that what we've done so far is based on well-formed security events because we are taking intrusion prevention system logs. What I'm proposing here is to look at telemetry directly, so it will be way more noisy and way more challenging. But that's what research is about. We need to challenge ourselves. But yeah, in general, I think that that this makes sense. We're trying to map semantic meaning of what you're observing into sequences of events, similar to what we're doing when we're looking at natural language, basically.
Yeah, that's interesting. Yeah, I'm just thinking that I think that can apply to many situations in the ops domain beyond just malicious attack.
Definitely, beyond security, yes. So a natural failure, an operating system failure or whatever could follow specific steps, build up to whatever, a catastrophe or something. So we could definitely leverage that. Yeah.
Cool. Let's see, we have a couple of questions here. To collect telemetry data, do you sit and try to hack and break your own systems? Presume not.
That's a great question. So, I mean, that's we talked about data, like telemetry, tracing, and all kinds of data, and we need also data about problems, right? So, I guess that's what the question means. Like, do we just sit and try to hack and break the system? Actually, yes. As part of our research, we did implement synthetic anomalies based on discussions with what a real anomaly would look like. We did replicate problems that appeared on national vulnerability database. We did replicate problems based on discussions with others. So whenever we can get real world problems from others, we can use them directly. And sometimes we actually do implement problems on purpose into the system. So the more we know about problems, like I mentioned before, the better. And the better, basically, more accurate our experiments will get. So we'd like to hear all kinds of comments about this from the community.
Cool. Yeah, we have another question here. So is attack2vec aware of the order in which the exploits can be used? So like if attack2vec were inspired by word2vec, that would make the embeddings unaware of the order between the words /exploits. Or is the context taken in spans left to right? More of a question about how attack2vec constructed in comparison to word2vec.
Yes. So it is aware of the ordering of events. It is also able to deal with noise to some extent, because when you are sitting on a computer and you're looking at security events, there may be unrelated security events that are happening, right? So there might be a real attack, and then there might be decoy attacks or other people doing random things, and so on and so forth. So to some extent, we're able to deal with that. Yes.
Cool. All right, so we're coming kind of towards the end of the time here. I think we can maybe open it up for more general questions and maybe return to some that were missed. One question that I have for all of you is, like, essentially, as academic researchers, what do you see as the benefit of being able to run these projects as part of the Operate First initiative and collaborate with an open source community?
Well, I mean, I think we emphasized this a few times, but having great ideas on analytics is great, but we can only do so much analytics if we don't have real world data. So Operate First enables us to put our methods in front of users right away, to this community right away. And not only that, but so we can get more feedback, more data. People run real-world applications on Operate First Cloud, so we can get real-world data and then put our frameworks in front of users right away, get more feedback, update as needed. So this is really essential, so that we are working on a platform where we have great visibility and observability and the like. So I don't know if Gianluca and Alan, do you want to say anything further?
Yeah, so just have one point to add, right? So by joining this community, right? So we're not only getting data, we are getting also the feedback about what are the most important, right? Different people have different, ideas and different opinions about what important, what metrics our analytics should support. We can gauge and gather this feedback and then put the most important things for up and running for operations, and also open source. As by my experiences, all the open source coders, programmers are hackers and top engineers, and their feedback to how to integrate to such a complex system will be a very valuable feedback as well. So we would like to work with these folks and to see, there's a bug in the code, and let's fix it. Let's make it more efficient. Maybe this bug can cost more, like 100 CPU cycle more for data processing. Let's fix it, right? So this bug cannot be easily captured by us. Yeah, thank you.
And maybe to add to it from my perspective. Oh, sorry, Gianluca, you go first.
Oh no, I just wanted to say that it's actually important for us to see what people who are working with these technologies every day consider being important problems, and what are the real problems that they are facing, right? So it's very easy for us to come up with our own fancy academic problems, but then have no application to the real world. So that's where this kind of projects actually come into play, and they're very valuable for us definitely, and I hope also for the community.
Yeah, and I'd like to add that I'm super excited about this because this is the first larger project really touching a lot of the moving parts in that really young community yet, where we actually combine some of the build pipelines, some of the platform monitoring, and some of the like the Jupyter notebooks. They are part of the user-facing applications. So this time we can actually go full circle across the stack, across the platform, and make something where it really takes a community to build something meaningful. And maybe that's also a good segue into a question that I have noted down here to the researchers. I understand that some of the stuff that you did is based on already existing code. And I figured, what do you expect the balance between implementing and researching new algorithms for sketches, for example, or new AI models for doing threats to VEC or something like this, versus the data engineering and integration problems? Like, how do I not just implement a sketch, but how do I integrate the sketches into a data collection tool like Prometheus, which doesn't support sketches yet? So that becomes more like an data engineering and an integration problem, and not so much a algorithms research problem. So what do you expect the balance would be there?
So that's a great point, right? So I think, even as researchers, I don't think I would say it's a balance, because I would say it's exploration, right? So we cannot just build an algorithm based on mathematical formula, and we have to understand what are the important things that we should measure, right? So I think it's a great motivation point. And then I think what really need to balance, you mentioned clearly, is once we got this motivation, I think this is the most important metric, and we done it our local test bed and done it seems quite accurately. We want to merge it and we want to integrate it into a more operation kind of level of system that we have to balance. We have to close working with UFox, with open source contributors to make it happen, right? So I think that's we would like to dedicate time for that, but I think the joint efforts will make it more efficient. So I want to add one example that we're working with the similar group, that we are trying to adopting some of the sketches into a famous open source library like DBDK. And even just a simple algorithm that took us a year to integrate and up and running, because every CPU cycle counts. So I think we wanted to say, we're probably not spending 100% time to optimizing one CPU cycle, but I think it would be pretty efficient that we work with UFox and we get feedback, and then we can fix it quicker.
Awesome. That's great. Yes, I'm also looking forward to being part of this as well. So yes, we only have 5 minutes left. I think we're going to have Marcel close us off. Some call to actions maybe about what people can do next if they're interested in getting more involved with Operate First or this particular initiative.
So I mean the links are on Aisha's and Alan's and Gianluca's slide here. It's this GitHub github.com operate-first/AI for Cloud Ops. That's the repository right now. If you want to be involved in it, go to that repository. I guess that will be populated with some of the slides here, some more materials. The planning will happen there, or at least links from that repository to where the planning and other things happen. It has a link to a Slack channel where the Operate First community hangs out. And if you want to contribute to that, jump over there. So I'm super excited for this happening because it's something real, right? And it's something that is evolving. And hopefully after 1 or 2 years, we still have something up and running, and it's not just slides and papers. I'm not discounting slides and papers. They're great and important, but I think it's also important to have something actual running for longer term and proof that it's there, because it's easier to introspect a physical car than just the blueprints of a car.
Yeah, and on that point of actually running stuff, and there's some questions in the chat around the current GitHub repository, where they can actually find the images to run some of the code that was discussed here, or even where the code for the Python packages are for some of the different tools like Praxis and Vaith. I'll say this is a new repository that we put together just to start this collaboration, but I assume in the next few days.
So, one clarification about that, Michael, thank you. So we already have some code out there for Proxy and ACE, and there are a couple of other repositories. Like we didn't discuss about Iterate, for instance, today, but there's that too. That's for online experimentation in the cloud. So you can access these things in the project website. There are links to it. And then if you are looking for a specific version or a specific image, let us know. You can create an issue in the Git or email one of us, and then we'll get back to you. Like while we are working on transferring these ideas and applying these type of ideas in the Operate First environment, if you want to use something right away, let us know, and we'll do our best to work with you.
Yes, thank you. Yeah, so I was just to say, with this repo will be updated with even more information soon. Great. Well, it's 3 minutes left. I think we covered everything we wanted to cover. If there's any other last minute questions or anything, or maybe I'll hand it back to Heidi at this point.
That's awesome. Thank you, Michael. I just wanted to point out, I put the link to the project page, the other project page that's not in Operate First, in the chat. And there are some project repositories in there you can look at for code that was done and is available. And anybody who has any questions, feel free to reach out through the Operate First webpage. We will be contributing there from the research group, or reach out to us in person, and we're happy to follow up on research ideas or implementation ideas, or just ways to make operations more open and transparent. So thanks everyone for coming. Really appreciate it. We'll share the video and the slides after the event, and send out announcements to folks who were here. Really happy to see so much interest in this and so much participation. Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye.